Hello class, welcome to your first video on geometric sequences. We've already completed a lesson on arithmetic sequences, also a lesson on arithmetic series. We've even talked about what it means for a sequence of numbers to be geometric in nature. So now we're going to get into all the details of geometric sequences. So our two learning targets for today are I can classify sequences as geometric and find the common ratio, and I can find the nth term of a geometric sequence. So just as a reminder, we first need to talk about what it means to be a geometric sequence. From a textbook, we read, a geometric sequence with a starting value A and a common ratio R is a sequence of this form. So we see a sequence in the form where you start with a number, and then you take that number and you multiply by R. R is the common ratio. Then if I multiply by R, that common ratio again, that's like multiplying the first number times R squared. And then if I multiply by R another time, that's like multiplying the first number times R to the third power. So the thing that we really need to remember when we're talking about geometric sequences is that we are multiplying by this common ratio R. There is a formula for geometric sequences that we see here. AN equals A1 times R to the n minus 1. Sometimes the formula is shown with these parentheses here, and that's even like that on the Quality Core formula sheet if you're using that. I prefer for us not to have those parentheses there, and we just consider the fact that we're going to take R, the common ratio, and raise it to the n minus 1 power. As a matter of fact, if I were going to put the parentheses anywhere, it would be just around R, and then you raise R to whatever that n minus 1 power. Now, this part, don't let that scare you. It says for n greater than or equal to 1. We know n represented the number of terms, and that just means there has to be one or more terms of the sequence. You can't have a negative amount of terms. Okay, so that's the formula, and we're going to get into some examples here. So our first question says, is the sequence geometric? That's a yes or no question. And then if it is, what are A1 and R? So first, let's determine if this particular sequence is considered geometric. Well, in order to determine that, if you remember in arithmetic sequences, we looked for a common difference by subtracting a term by the term in front of it. For geometric sequences, we're going to divide by the term in front of it. So if I begin by dividing 6 divided by 3, we get a R equal to 2. Try that again. Try 12 divided by 6, and we still get R equal to 2. And if I divide 24 by 12, so doing that a third time, I still get R equal to 2. And one last time, 48 divided by 24 is also 2. So you'll notice here that we have this common ratio R, which is 2. That is the number that we multiply by to get the next term of the sequence. I would say yes, this is geometric because I had a common ratio, and A1 is still going to be referring to the first term of the sequence. So A1 in this sequence is 3. If I were asked to extend the sequence, could we find the next number in the pattern? Sure, if the common ratio is 2, we take that 48, we multiply by 2, the common ratio, and the next number would be 96, and so on. Next question, is the sequence geometric? If it is, what are A1 and R? So again, we're going to do our division. 6 divided by 3 is 2. 9 divided by 6 is 1.5. Is this geometric? Because that ratio is not the same ratio both times, we would say that no, this is not a geometric sequence. Okay, the next one is looking at this in exponential terms. So one method is I could convert all of these to their numbers that they refer to. 3 to the 5th power is 243. 3 to the 10th power is 59,049. 3 to the 15th power is 14,348,907. And so on. And then do my division to see if I get a common ratio. But that probably is a little bit more work than necessary if you understand exponent rules. So I'm looking at just the exponents here. Do you notice a pattern in the exponents? If you notice an arithmetic pattern in the exponents, you keep adding 5. And the significance here is that in multiplication, we add exponents. So if you see an arithmetic pattern in exponents, then that really means you're dealing with a geometric sequence. Let me elaborate. Three to the 5th power times 3 to the 5th power equals 3 to the 10th power. Because in multiplication, we add exponents of like basis. If I take 3 to the 10th power and multiply by 3 to the 5th power, I will get 3 to the 15th power, because in multiplication, I add exponents of like basis. 3 to the 5th power, 3 to the 15th power times 3 to the 5th power would give me 3 to the 20th power, because in multiplication we add powers of like basis. So if we'll look, there's my first term, there's my second term, there's my third term, there's my fourth term. How did I get from one term to the next? I multiplied each time by 3 to the 5th power. So I would say yes, this is geometric. If it is, what is A1? A1, my first term, was given to be 3 to the 5th power. And R, my common ratio, is the number that I multiplied each term by to get the next term of the sequence. That's also 3 to the 5th power. Okay, next question. Is this sequence geometric? If it is, what are A1 and R? So I'm going to perform this division. 5 divided by 1 is 5. 9 divided by 5 is 1.8. Because that division did not produce the exact same ratio, we would say no, this is not geometric. Okay, now our learning target changes. It says I can find the nth term of a geometric sequence. Well, if I'm looking for the nth term, I'm just looking here to extend the pattern that's given. So I need to first decide what is this pattern. It says it's geometric, so I'm going to do this division. 30 divided by 20 is 1.5. Check that here. 45 divided by 30 is also 1.5. So we have a common ratio of 1.5. R is 1.5. So in order to extend the pattern, we're going to multiply by 1.5. So 45 times 1.5 is 67.5. And then again, I'm going to multiply by 1.5. And I get 101.25. This is how we can extend a geometric sequence. Here we're asked again to extend a geometric sequence. And I want you to look carefully at this geometric sequence. We see a positive, a negative, and a positive. And we might immediately think, you know what? I don't think that this has a common ratio. But let's check that with division. Negative 16 divided by 64 is negative 0.25. And 4 divided by negative 16. Notice I have to type this number in first, and the number in front of it is what I divide by. 4 divided by negative 16 is also negative 0.25. So I do have a common ratio, and because my common ratio is negative, what we're going to find is that the terms of the sequence are going to go back and forth from positive to negative to positive to negative. So with a common ratio of negative 0.25, I'm going to multiply by negative 0.25. So 4 times negative 0.25 gives me a next term of negative 1. And then I'm going to multiply that by negative 0.25. And I get a last term of positive 0.25. Notice here that that pattern of positive, negative, positive, negative, positive continues. So anytime our common ratio is a negative number, negative 0.25, then what we will find is that the terms of the sequence will go back and forth from positive to negative, to positive to negative, anytime R is a negative number. This problem says to find the first 5 terms in each geometric sequence. So I'm going to find the first 5 terms. Well, the first term is given. A1 is given. So I'm going to find A2, A3, A4, and A5 by using that the first term was negative 2 and my ratio is 3. So I find A2 by saying negative 2 times my common ratio. So negative 2 times 3 gives me A2 to be negative 6. And I multiply that by 3 to get A3 to be negative 18. And I multiply that by 3 to give me that A4 is negative 54. And I multiply that by 3 to give me that A5 is negative 162. So the first 5 terms of this of this geometric sequence are negative 2, negative 6, negative 18, negative 54, negative 162. I do want to point out that I started with a negative and I stayed in the negative the whole time. I had negative numbers. That is going to be characteristic of any time R is positive. If R is positive, you're going to keep the same sign as A1 in the entire sequence. Whereas when R is negative, the terms alternate signs. From positive to negative to positive to negative to positive to negative. So that's big stuff. That's big stuff to understand. So if R is positive, common ratio is positive, you're going to keep the same sign as A1 through the entire sequence. If R is negative, then the terms are going to alternate signs back and forth. Looking at the next one, it says to find the nth term in the geometric sequence. So this is getting a little bit tougher. This time they're telling me that A1 is given to be 7, that R is 2, and they're asking me to find the nth term. 1, 2, 3, 4. So I'm looking for this fourth term, A4. All right, well, if I know my common ratio is 2, I can take my first term and multiply by 2 to get 14. And take my second term and multiply by 2 to get 28. And take my third term and multiply by 2 to get 56. So A4 is equal to the number 56. I do want to mention that that was easy to find the fourth term, but if I had been asked to find the 40th term, I probably would not have wanted to create these blanks all the way out to the 40th term. So that is the reason that we prefer to have a formula. When the sequence goes out to really far into the sequence, then we prefer to use a formula to get our answer. So we're going to be looking at that as we move forward. Okay? This one is just asking us to go to the 6th term. I don't think it's necessary to use the formula here. I think I can use my blanks, especially when A3 was given to me. So A3 is 32. A4, A5, A6 is what we are told to find. So if the common ratio is negative 0.5, 32 times negative 0.5 would give me negative 16 for A4. And negative 16 times negative 0.5 would give me positive 8 for A5. And 8 times negative 0.5 would give me negative 4 for A6. So to find this nth term, if n is 6, I'm looking for the 6th term. They gave me the 3rd term. I was looking for the 6th term, so I only had to find 2 numbers in between to get there. Okay, this time you're given the 4th term. You're given A4. A4 is 108. We would go to A5, A6, A7, A8, A9, A10 will be here. And the common ratio is 3. So 108 times 3 is 324. And 324 times 3 is 972. And 972 times 3 is 2,916. And 2,916 times 3 is 8,748. And 8,748 times 3 is 26,244. And 26,244 times 3 gives me that the 10th term of this geometric sequence is 78,732. Now you may say that's a lot of really large numbers to find, and perhaps a formula would be a smarter way when we're dealing with such huge numbers. So let's take a look at what the formula would do for us here. So if I were to use the formula, I would start with AN equals A1 times R to the n minus 1. A1 was not given in this example, but I would consider this A4 to be A1. And if I subtracted 3 from that, this would be equivalent to finding the 7th term. So this would be like A1, A2, A3, A4, A5, A6, A7. So it would be equivalent to finding the 7th term. So see, I subtracted 3 from 4, I subtract 3 from 10 and find the 7th term. So this would be like finding A7, where A1 given is 108. The common ratio we are given is 3, and we're finding the 7th term. So we substitute in like that. Now here, it's very easy to go immediately into the calculator, and we could say 108 multiplied by parentheses 3, close parentheses, raised to the power of 7 minus 1, or you could just input a 6 there. I have a typo. And we get the same 78,732. So the formula is pretty great. It did save us from finding, would have saved us from finding a whole lot of super large numbers along the way. So we're going to be jumping into that with the next few examples. Okay, so here, it's asking me to find the indicated term of the geometric sequence. It asks me to find the 14th term of this sequence. Let's begin by writing down our formula. AN is equal to A1 times R to the n minus 1. Well, can you indicate to me what A1 is in this sequence? If you said 4, you're right. A1 is 4. Can you tell me what the common ratio is in this sequence? Well, we're going to divide. 12 divided by 4, that's 3. 36 divided by 12, that's 3. So R is exactly 3. And if we are asked to find the 14th term, that is our n. So from here, we can find A14 by substituting this expression into the calculator. So 4 times, parentheses 3, raised to the power of 14 minus 1. And you can use your calculators at your desks. Whoa, baby. It's big. One of the characteristics of geometric sequences is they get really big really fast. Why are geometric sequences getting big so fast? We're just going to the 14th term. Did you guys get a super large number on your screen? They're getting really big really fast because we're multiplying by a factor, whereas in arithmetic sequences, we were just adding a number, and multiplying grows much faster than addition will grow a number. So our 14th term, I said A4, our 14th term of this sequence is 6,377,292. Check your work with mine. Okay, let's look at the next one. Find the 12th term of the sequence. I want you to pause I'm going to pause the video. I want you to try this on your own using the formula A1 times R to the n minus 1. Go ahead and pause now. So you can check your work with mine. If you got 1,594,323, then you're rocking it. You're getting it right. 14, find A9 for the geometric sequence. Go ahead and pause and try this one on your own. So this one was pretty yucky. If you look at it and notice that the terms are actually decreasing, And when you do this division, 30 divided by 60, we get a common ratio of 0.5. So our R here is a decimal, 0.5, or a fraction, 1/2. So A1 was 60. We're looking for A9, so we substitute in 9 for N. And when we get this really nasty decimal, 0.234375. But you may know that a calculator trick, if you don't like the answer as a decimal, or if maybe you're taking a multiple choice test and decimals are not a choice, you can tap math, enter, enter. That is math, enter, enter, and that converts it to this fraction for us. So we can say that the 9th term is this ugly decimal or this ugly fraction. So I hope that this lesson has helped you to understand a little bit more deeply about geometric sequences, how to extend a pattern, how to find a common ratio, and how to use the geometric sequence formula. Good luck with your assignment.